Now, we look at the case where the data is not so well behaved as we would want it to be, right. Specifically, the data is not separable, right, is not linearly separable. So, we look at the not separable case. So, I am going to introduce some additional data points to whatever we have been looking at so far, right. So, so, this is a non-separable case, right, linearly non-separable case, because some of my data points are really mixed up here, right. So, I would still like to have a large margin, but not only am I allowing data that is not separable, but I am also allowing data points to fall within the margin. So, it is essentially two sides of the same coin, right. So, if I am allowing data to fall within the margin, so in some sense I am having the flexibility to make some kind of errors as well, right. So, I essentially look at how far away am I from the margin, right, in the wrong direction, right. So, I am going to denote these distances by which I am away from the margin by the symbol zeta, right. So, we still have our same constraints here, but now going back to our optimization problem, what I am really looking to do here is I am going to modify my constraints such that, so yi times xi transpose beta plus beta naught, right, is really greater than or equal to one minus zeta I, where zeta I is some kind of a slack variable, okay, that allows me to satisfy this constraint with some error in it. So, essentially if you look at this first data point that I drew here, if you look at the first data point I drew here, right, so it has a slack of zeta 1, right, and the second data point has a slack of zeta 2, right, and this one has a really fairly large slack, but still it is possible under the circumstances. So, this allows me to have a larger margin, right. So, if you think about it, if I did not, let us say even if this data point was not there, if I did not allow these kinds of data points to appear in the margin, right, if I did not allow these things to appear in the margin, my classifier would actually have been here, right, my classifier would have been here trying to separate this x and from this O, right, and the margin would have been very small, and in all likelihood I am fitting a noise data point here, which is not an optimal thing to do, right. So, now by allowing some amount of data points to fall within the margin, right, I am able to expand the size of the margin that I can have, and I can also incorporate linearly the small number of errors that I have to make because the data is not linearly separable, right. But then I do not want this to become arbitrarily large, right. I just cannot say that hey, it does not matter, you can have a slack variable for every data point that you have, and the slack variable can be as large as you want it, right. So, I need to have a control on this as well, and therefore, I I try to minimize that, right. So, are these conditions sufficient for us to define a new problem now? There is still one more condition that we need. So, we are really measuring zetas in one direction and not in the other direction, right. So, we have to be careful. So, I also need to add another set of constraints. Let us say that the zetas have to be positives. So, that is the complete constraint optimization problem for us in the case where the data is not linearly separable. So, you have to minimize beta squared, norm beta squared plus the sum of the zetas that you are using, subject to the condition that the yi xi transpose beta plus beta naught is greater than 1 minus zeta I and zeta I is greater than or equal to 0. So, what happens to our primal objective function now? So, you notice that we need a component that corresponds to the actual objective function and we need a component that corresponds to the constraints that we are using, right. So, the first part of it remains as it is, right, but then we have to add the newer components that we are bringing in. Right. So, this is the second part of the objective function and this is the first constraint, right, and this is the second constraint, and since this has to apply to each and every data point. So, you have the summation over all the data points there. Likewise here. So, how do we go about deriving the dual in this case? So, just like we did earlier, so we start differentiating the primal with respect to the various parameters. So, you end up with the same condition that you had earlier, okay, and here you end up with the same condition. Then when you differentiate with respect to the zetas, you end up with so one condition for each I, right. So, alpha I equal to C minus mu I, right. So, I can put everything back in to the primal, do some algebra and derive my dual, which turns out to look exactly like this, except that my alpha has to lie between 0 and C, that you can actually see from that condition that we have there, right. And alpha I y i's have to be equal to 0, that we already have as a condition. So, the remainder of the KKT conditions that we have, I am just going to go through this very quickly because I do not want to do the complete derivations here. So, the remainder of the KKT conditions would be this is what we had last time except for the zeta I part, right, but you also have which is essentially our initial constraint written in a slightly different form, right. So, the third constraint here is just the original constraint with the 1 minus zeta is taken to the other side, right. So, what is this that you notice from here? So, let us go back and let us do the same argument. If alpha is greater than 0, then yi xi transpose beta naught is actually less than 1, right. Only then this will be 0, because right. So, that would mean that for the particular choice of zeta i's, so this goes to 0, that would mean that this is on the wrong side of the margin, right, or on the margin, right. So, it will be lesser than or equal to 1, right. Either if zeta i's are 0, then it will be on the margin. If zeta i's are non-zero, it will be within the margin. So, all the data points that are one side of the margin are all support vectors, right. Because again, like last time, so betas depend only on those vectors for which alpha I is greater than 0, right. So, if the data happens to be on the right side of the margin, right, then your alpha i's have to be 0, as we saw earlier. Right. And so, those data points have no role in computing. So, this essentially kind of takes us over the entire optimal separating hyperplane part, right. So, when it was linearly separable, so we had a very easy solution, but when the data is not linearly separable, and so we have to allow for the possibility of data points to lie on the wrong side of the margin. So, when we do that, we can essentially take advantage of the fact and try to push our margin away by allowing data points which are correctly classified, but are within the margin. A small fraction of such data points are permitted, and therefore, that allows us to expand the margin a little bit, right. And so, we can come up with a solution. So, you do not have to at this point you do not have to worry about the details of solving this optimization problem, but there are many powerful optimization techniques that have been developed that allow you to solve these kinds of problems. And in fact, SVMs have led to the revival of a popular class of optimization algorithms called interior point methods, because they were very efficient in solving these kinds of optimization problems. And they are pretty robust classifiers and very widely used for a very wide variety of applications, right. But some of you are probably thinking right now, but whenever I talk about support vector machines, people always tell me something about kernels, right. And I thought support vector machines were all about kernels, and I have not talked about kernels at all at any point here. Yes, so the kernel idea is very crucial in support vector machines, and I will be looking at that in more detail in the next module. But what you should remember is the basic optimization problem that you are trying to solve with support vector machines is the one of optimal separating hyperplanes. Okay. So, in fact, the kernel idea is called the kernel trick, because it allows you to solve a really wide variety of problems which are not easily amenable to linear classification by using a very powerful idea, but then the underlying optimization problem that you are solving is still the same optimization problem that I have written out on the board so far in the last two modules.